Welcome to part 2 of Le Chatelier's principle. We're going to go over some practice questions regarding Le Chatelier's principle. We're going to review the stresses on equilibrium and how those equilibrium are going to respond to said stresses. Here's our first example. So we have hydrogen gas plus fluorine gas making hydrogen fluoride gas. In this case, we're going to change the concentration. So our stress is we're going to add hydrogen fluoride to the system. When something is added to the system, the equilibrium is going to shift in order to return back to as close to the original state as it can get. So if we have extra hydrogen fluoride, we're going to get rid of the excess fluoride by favoring the reaction where hydrogen fluoride is used as a reactant. So in this case, we're going to favor the reverse reaction. This reverse reaction is going to decrease the hydrogen fluoride concentration while producing more hydrogen gas and fluorine gas. Our next example, we're going to look at what happens when we decrease the concentration of something in an equilibrium. So we're using the same equilibrium, and this time we're going to remove fluorine gas and decrease the concentration of the fluorine gas. When a reactant or product has a decrease in concentration, our equilibrium is going to shift in a way to replace it. So we have to replenish what is lost. So in this case, we're going to favor the reverse reaction where we are producing fluorine gas. So again, we're replenishing what is lost. This means we're going to see an increase in fluorine gas, so we're returning back to that normal state, quote unquote. We're going to see an increase in concentration of hydrogen gas as well, because both of these are being produced. And we're going to see a decrease in hydrogen fluoride gas because it is being used up in order to replenish what has been lost. Alright, so now it's your turn to try. So we have the given equation, nitrogen gas plus hydrogen gas making ammonia gas. This is Haber's process. Hopefully you remember that from the last video. What occurs when the concentration of hydrogen gas is increased? When hydrogen gas is increased, our equilibrium is going to shift to use up the excess hydrogen gas. So we're going to see a shift to the right. This way, the extra hydrogen gas is being used up. So let's see, that gets rid of options A and B. It has to be C or D, right? Shift to the right. When it's doing so, the concentration of N2, so we're using nitrogen gas and hydrogen gas to produce ammonia when we're favoring the forward direction. This means N2 and H2 are going to decrease in concentration, making C our correct answer. Let's talk about our next stress, which is going to be heat. So equilibrium are going to respond to changes in temperature. A reminder that heat can be shown a few different ways in a chemical equation. You could see plus heat, you can see plus a numerical value like we have here, so 73 kilojoules is representing our heat. And you could also see delta H, meaning our heat of reaction, as our variable for heat. Another reminder, we have heat on the reactant side of the equation. This means this is an endothermic reaction. Heat is being added to our reactant, endothermic. If it was exothermic, it would be listed as a product on the other side. So for example, our stress is there is a decrease in heat. Our system has been cooled down. Very much like concentration, you can pretty much treat temperature as another reactant or product, but when we see a decrease in heat, that heat has to be replenished by the equilibrium. It's going to try to return back to its quote-unquote normal state. So in this case, to replenish what is lost, we're going to see a shift to the left. We're favoring the reverse reaction. This results in a decrease in hydrogen and bromine as they are used up to replace our heat. So we're going to see an increase in heat and we're going to see an increase in hydrogen bromide gas. On to the next example. So we have the same equilibrium, but this time there's going to be an increase in temperature. So we see an increase in temperature when there is an excess of something. Our equilibrium is going to shift to get rid of that excess. So that means our excess heat is going to be treated as a reactant so that we can get rid of it. And we're going to see a shift to the right, or we're going to favor the forward reaction. When favoring the forward reaction, we're going to see an overall decrease in energy, so getting rid of that excess reactant, a decrease in hydrogen bromide, and we're going to increase the concentration of hydrogen and bromine gas. Now it's your turn to give this a try, but given the equation represented at equilibrium, we have hydrogen gas, iodine gas, plus heat, becoming HI. Which of the following changes favors the reverse reaction? I'm going to go through each option here, but starting with A, decreasing the concentration of HI. If we decrease the concentration of HI is going to have to be replenished in the equilibrium, so we're going to see a right shift. This does not favor the reverse reaction, it favors the forward, so it cannot be our answer. Decreasing the temperature, if we decrease the temperature, our heat is going to have to be replenished by the equilibrium. We're going to see a shift to the left, favoring the reverse reaction, and that should be our answer. But just to make sure, let's take a look. C, increasing the concentration of iodine. If we increase iodine, we're going to have to get rid of the excess, which causes a shift to the right, favoring the forward reaction. And lastly, if we have a decrease in, an increase in pressure. A reminder, when looking at pressure, you're going to have to compare the amount of moles of gas on either side of the equation. In this case, we have 1 plus 1, 2 moles of gas. And we have 2 moles of gas on our product side. So increasing the pressure will actually have no effect. There will be no shift because we have an equal amount of gas on either side of our equation. Example 5, so we have 2 ozones becoming 3 oxygen in equilibrium. We're going to talk about our next stress, which is pressure. So I just touched on it a little bit in the last example, but pressure is only going to affect gases. So for example, let's say this said that both of these were liquids. Pressure would have no effect on the equilibrium. It only affects gases, and only affects gases in the equilibrium. So if this had plus solid sodium, the sodium would have no effect. But every time you're addressing pressure, you have to look at how many moles of gas are on your reactant side and your product side. So we have, again, 2 moles of gas on our reactant side. We're looking at the coefficient. We have 3 moles of oxygen molecules on our product side. When we add pressure, we're going to shift towards the least moles of gas. So an increase in pressure, that means a decrease in volume. There's less space for this equilibrium to occupy, so it's going to shift towards the least number of gas molecules. In this case, our reactant side has the least number of gas molecules. There's only 2 moles of gas molecules. So this is going to favor the reverse reaction. That means we're going to see an increase in concentration of ozone and a decrease in concentration of oxygen gas. On to our next example. So we're going to use the same equilibrium and we're going to remove pressure this time. So again, once you see something to do with pressure, we're going to count the moles of gas on either side of our equation. We have 2 moles of ozone, 3 moles of oxygen gas. When we remove pressure, we're going to shift to more moles of gas. If we remove pressure, so decrease in pressure, we have an increase in volume, meaning we have more space for our equilibria, right? Boyle's law, tells us they're inversely related. So we're going to see a shift towards more moles of gas. In this case, our product side has more moles. So we see a right shift favoring the forward reaction. That means our equilibrium is going to produce more oxygen. So we see an increase in oxygen and a decrease in ozone. Now it's your turn to give this a shot. So we have this equilibrium. If the pressure on the system is increased, what will happen to the concentration of chlorine gas? So again, when addressing pressure of a system, we're going to have to look at how many moles of gas on either side of our arrows. So here we have 4 moles of hydrogen chloride, 1 mole of oxygen gas for a total of 5 moles of gas on our reactant side. We have 2 plus 2, so 2 moles of chlorine plus 2 moles of water for 4 moles. Pressure is increased, so we're going to have a shift towards less moles of gas. So in this case, we're going to favor the forward reaction because our forward reaction produces the least amount of gas. This means that we are producing chlorine, so we should see an increase in concentration of chlorine. Alright, so we're almost finished here, but the last thing that I want to address is what effect does a catalyst have on an equilibrium? So if we have a system at equilibrium and we add a catalyst to the system, just a reminder, a catalyst is not in our balanced equation. It is a separate substance that is added, but it is not listed in our actual chemical equation. But the addition of a catalyst is going to change the forward and reverse reaction rates. It is only going to decrease the activation energy, just like we talked about, create that alternative pathway, which allows the rate of the forward and reverse reactions to be quicker. The effect of this is we're going to see that our equilibrium will be reached quicker just because those reactions are occurring faster. But overall, we're not going to see any change in concentration of our reactants or products. And it should have no effect on our equilibrium. What I mean by that is adding a catalyst will not cause any shift in the equilibrium. So the only thing we're going to see change is our rates are going to increase, our activation energy is lowered, but overall our equilibrium remains the same. Alright, and here's our last question. So given the equilibrium, we have A plus B making a compound of A and B plus heat. It is an exothermic reaction because heat is on our product side. Which change will not affect the equilibrium concentration of A, B, and A2B3? So let's go through each one. If we add more A, increasing the concentration or decreasing the concentration of any products or reactants will always cause a shift. So you can pretty much automatically dismiss this one, but if we add A, we're definitely going to see a right shift to get rid of that excess. Increasing the temperature is always going to affect our equilibrium and the concentrations, but if we increase the heat, we're going to see a shift to the left. This will increase the concentration of A and B and decrease the concentration of A2B3. Adding a catalyst sounds great because it shouldn't have any effect on the concentration. It only affects the rates of reaction. But let's check our last option still. Increasing the pressure, so we have 5 moles of gas on our reactant side, 2 plus 3. 1 mole of gas on our product side. Increasing the pressure will show a shift to the right towards our least moles of gas. That leaves us with our answer as, that should say C, hold on. There we go. So that should show our answer as C, adding a catalyst. Catalyst will not affect our equilibrium concentration and will not cause a shift left or right. It'll just affect our rates. If you have any questions, let me know. There will be practice questions on this soon.